Hello everyone, this course is the continuation of the previous course. I solved some problems about domains of functions in the previous one. In this course, I will solve again some problems about sketching of graphs of functions, and I will determine inverses of functions. Now, let's start with an example. Sketch the graph of exponential functions f and g. Of course, I will not use derivative rules to determine graphs of f and g. I will give some numerical values to x and see what will happen to f and g. For instance, for the function f, when x is minus 2, f is 1 over 4. When x is minus 1, then f is 1 over 2, etc. Let's mark all these points on the xy axis and see what do we have. When x is 2, f is 1 over 2. We have this point. When x is minus 1, y is 1 over 2. When x is 0, y is 1. This point. When x is 1, y is 2. We have this. And finally, when x is 2, y is 4. We have this point. Joining all these points, we have the graph of f. Is graph of exponential function f. What about graph of g? We will do the same thing for sketching graph of g. For instance, when x is 0, we have 1 for g. I will mark all these points on the xy axis. When x is minus 2, g is 4. This point. When x is 1, g is 2. When x is minus 1, g is 2. When x is 0, g is 1. Intersection point. When x is 1, g is 1 over 2. This point. And finally, when x is 2, g is 1 over 2. We have this point. Joining all these points, we have the graph of function g. G of x, which is 1 over 2 to the power x. If we choose more values for x, then we will have more precise graph for the functions f and g. Second example, let g is 4 minus exponential x over 2. Use transformations to explain how the graph of g is related to the graph of exponential x. f1 is exponential x. If we divide x by 2, then we stretch f1 to f2. If we multiply f2 by minus 1, then we reflect f2 in the line x-axis. Then we have x3. If we add 4 to f3, then we push f3 4 units to up. Then finally we have 4 minus exponential x over 2, which is g. So if we apply all these transformations to f1, which is exponential x, finally we have 4 minus exponential x over 2. Third example, sketch the graph of absolute value x squared plus 3x plus 3. Let's first sketch the graph of y equals x squared plus 3x plus 2 without absolute sign. We can write y as the multiplication of x plus 2 and x plus 1, since we have this. And if x is minus 2 or x is minus 1, then y is 0. So we have two intersection points. When x is minus 2, y is 0. When x is minus 1, y is again 0. We also have when x is 0 in this equation, y is 2. So the last intersection point is for 0, y is 2. We also need to find focus point of the parabola x squared plus 3x plus 2. To do this, we need to remember the formula for the x point of the focus. The formula for the x point of the focus is minus b over 2a. In our case, b is 3 and a is 1. So x is minus 3 over 2 is for x. If you put x in this formula, then y is minus 1 over 4. So focus point of the parabola is minus 3 over 2 minus 1 over 4. Let's mark all these points on the xy axis here. This is T point, focus point, and minus 2, 0 is here, minus 1, 0 is here, and finally the point 0, 2 is here. Joining all these points, we have the graph of parabola x squared plus 3x plus 2, but we need to find absolute value of x squared plus 3x plus 2. What can we do? We should focus on the graph of y, which is below of the x-axis. And we only carry this part to above x-axis. And we do not change other parts of the graph. On the right hand side is colored by green one, is the reflection of below of the graph in the line x. Okay, let's try to understand with one more example. Sketch the graphs of given absolute value functions. We have a parabola x squared minus x in the first one. Is the graph of parabola absolute value of x squared, is the graph of parabola x squared minus x. Since we have absolute sign, we focus on the graph of x squared minus x, which is below of x-axis, and we will carry this part to above of x-axis. And then we have graph of f, which is absolute value of x squared minus x. We will use the same idea in the problem B. It is known that is graph of x cube. Since we have absolute value, we carry this part to above x-axis. So it's symmetric in the line x-axis. Now let's find inverse of functions. In this problem, we have x squared minus 2x plus 2. As you see, it's not possible to make x alone in this form. So we first must substitute the expression. We can write x squared minus 2x plus 3 as x minus 1 squared. If we do this, we have x squared minus 2x plus 1. So we need to add 2 plus 2. So we have 1 minus 2 is equal to x minus 1 squared. Let's take the square root of both sides. We have x minus 1 is equal to square root y minus 2. This implies that x is 1 plus square root y minus 2. But do not forget here that when we take square root of both sides, we have absolute value for x. So we have two cases for x. One of them is x minus 1. X minus 1 is directly equal to square root of y minus 2. So we have this. Or x is 1 minus square root of y minus 2. So we have two inverses for the function f. Let me give more detail for this problem. Since absolute value of x minus 1 is equal to square root of y minus 2, I said we have two cases. Let me now explain. The first case is x minus 1 is equal to square root y minus 2. And second case is x minus 1 is equal to minus square root y minus 2. By these two cases, we have two inverses for the function f. Now we have a new example. Find the inverse of f, which is defined by x cubed minus 6 x squared plus 12x. We must substitute this expression. Let me first write the expression. We must add and subtract something to get x minus 2. We must write x minus 2 parentheses plus 8. If we add and subtract 8 to the equation, we have this equality. This implies that y minus 8 is equal to x minus 2 to the power 3. And take the cube root of both sides. We have cube root y minus 2 is equal to x minus 2. In this problem, we do not need an absolute sign for the right hand side function. This is why we have x is equal to 2 plus y minus 2. So inverse of f of x is 2 plus cube root y minus 2. As you see, it seems a more complicated problem, but it does not. We have another example. Show that the curve y is equal to ax plus b over cx minus a is symmetric in the line y equals x. To solve this problem, we must show that inverse of f is equal to f, since f and inverse of f is symmetric in the line y equals x. So, if we can show inverse of f is equal to f, then we can say that this line is symmetric in the line y equals x. Now, let's try to find inverse of y. Y is ax plus b over cx minus a. Let's substitute this expression. We have cxy minus ay is equal to ax plus b. Or we have, let's take the parentheses of x, then we have cy minus a is equal to ay plus b. We took the parentheses of x. So x is ay plus b over cy minus a. As you see, inverse of f of x is ax plus b over cx minus a. Since inverse of f is equal to f of x, this line is symmetric in the line y equals x. In this example, it's requested to show that inverse of an increasing function is also increasing. Let's first remember what is an increasing function. Okay, let us suppose that let f be an increasing function. So let's remember the definition of increasing function. F of x1 is smaller than f of x2 for each x1 is smaller than x2. If we have this case, we say that the function is increasing. Let's assume that we have this case. Also let f of x1 is y1 and f of x2 be y2. So y1 is smaller than y2. Why do we have this? Since f of x2 is greater than f of x1, y2 is greater than y1. Let's continue. Since f inverse of y1 is equal to x1 by this, and f inverse of y2 is x2 by this equality, we have this inequality. F inverse of y1 is smaller than f inverse of y2. We have this result since x2 is greater than x1. x2 is greater than x1. So, inverse of an increasing function is also increasing. We have a similar kind of example. Show that the following statement is true. F is increasing implies that f is 1-to-1. Okay, let's start. If f is increasing, we have f of x1 is smaller than f of x2 for each x1 is smaller than x2. So we have two cases here. We have two cases. The first case is x1 is smaller than x2. And the second case, x1 is greater than x2. For the first case, since f is increasing function, this statement implies that f of x1 is always smaller than f of x2. So it means that f of x1 is always different from f of x2. So it's 1 to 1. What about second case? Since f is an increasing function and x1 is greater than x2, f of x1 is greater than f of x2. It implies that f of x1 is not equal to f of x2. For both cases, we have f of x1 is not equal to f of x2 for each x1 is not equal to x2. So when f is increasing function, f is also 1 to 1. Okay, let's finish this course with two logarithm problems. Solve the given equation. Let's first substitute the equation. Logarithm base 4 to x plus logarithm base 4 x minus 3 is equal to 1. Using the properties of logarithm function, we have logarithm base 4 x times x minus 3. Because of this addition, we transform the addition to multiplication is equal to 1. Let's continue to substitute this inside of the parentheses of logarithm. We have x squared minus 3x is equal to 1. We know from the properties of logarithm function 4 to the power 1 is equal to inside of logarithm, which is x squared minus 3x. Let's substitute this equality. We have x squared minus 3x minus 4 is equal to 0. So let's find the roots. X is either 4 or minus 1. So we have two roots for the logarithm, but be careful here, x cannot be minus 1. Just look at the left hand side of the equality. We have logarithm base 4x, and inside of logarithm never ever can be negative, can take a negative value. So we do not have minus 1. Only for the point 4 this equality satisfies. This is our last example for this course. Solve the equation of exponential function. In this problem, we should change the variable. Instead of exponential x, I change the variable. Write t instead of exponential x. So the equation becomes t minus, instead of exponential minus x, we have 1 over t is equal to 2. If we substitute this expression, we have t squared minus 2t minus 1 is equal to 0. Just remember the formula of finding roots of equations. We have two values for t. The first one is 1 plus square root 2, and the second root is 1 minus square root 2. But again, be careful here. T is exponential x, and exponential x always positive. So this implies that t is always positive. So the second root is not possible for the equation. The only root is t1. Let's go back. Since exponential x is t and t1 is 1 plus square root 2, we have, take the ln of both sides, we have ln exponential x is equal to ln 1 plus square root 2. ln exponential x is x, so x is equal to ln 1 plus square root 2 is the solution of the equation.